Hello everyone. Today I want to present exploring the CPU and FPGA heterogeneous execution with the Coexecutor runtime. My name is Maria Angelica Dávila and this work is developed in collaboration with the University of Zaragoza and the University of Cantabria. To start, I want to talk about heterogeneous systems which are present in different fields of computing from mobile to supercomputing. This system includes a set of devices with different architectures to improve computation and energy efficiency. The most typical devices are the CPU and the GPU, and more recently the FPGAs are being included. Heterogeneous systems are still important today since the chip designs has faced physical limitations to continue reducing the transistor size due to power limitation, meaning this the end of an era and then are scaling predictions. Although with the heterogeneous system the computing performance could be improved, program different architecture is a challenge, since every device has its own architecture, memory, frequency, and others. And to program it requires different language and tools, requiring different expertise from programmers. It's precisely here where the inclusion of a new programming model as one API can help programmers in unifying the programming tools for accelerator in heterogeneous systems, being this an advance in programmability. But one API left a high-level layer to allow load balancing among devices, being the load distribution process manual and tedious. Here is where the Coexecution runtime is very useful. In this work, we include an FPGA, which is a device that can give better performance than a GPU or a CPU, but traditionally are difficult to program. As an agenda of this video, I'm going to talk about the state of the art, talking about the FPGA, their programming, the parallel for parallelism, and the one API tool. After this, I'm going to talk about the Coexecutor that includes the CPU, FPGA to make load balancing. After this, I'm going to talk about the methodology, the results, and finally the conclusions. FPGAs are an array of configurable logic blocks that are mainly attractive for the programmable routing, which provides a high flexible architecture for application-specific hardware. They are composed by columns of reconfigurable logic, DSP blocks, and internal scalable memory. The FPGAs are in the middle ground between general-purpose processors and ASIC, often providing better performance per watt in comparison with a CPU. The evolution of programming in FPGAs from traditional hardware description language to high-level synthesis supposes for software engineers a reduction in the design effort with more compact and less event-prone implementation and requires low hardware expertise. Kubernetes tools are more friendly, using languages as C, C++, OpenCL, and recently Secret that is using one API to program and validate the implementation. After validation, the SLS tools can transfer the code into an HDL code to generate the FPGA bstring. Now, I am going to talk about the parallel for pattern used to distribute the workload in devices. The parallel for structure allows to express the independence in a mode iteration. For example, in a traditional for loop in C++, the iteration runs sequentially. Instead, in a parallel for pattern, it can exploit the parallel threads in a device. The parallel for is ideal for partitioning workload remote devices, for example, one part to the CPU and the another part to the GPU. One API supports the parallel for pattern as this code shows, to express parallelism inside devices, with the advantage that it uses a single high-level source code for different kinds of devices. Unfortunately, the one API runtime does not support the parallel for among devices. Another problem that we have to face when an API is the difference with FPGA programming. The FPGA uses a ahead of time compilation since the process is long, being with hours and days. Theoretically, the one API can link different devices using the one API linker in one fat binary. This sounds good for load balancing with CPU and FPGA, But during the development of this work, we found that this linker doesn't support no one device when an FPGA is used. Now I'm going to talk about the Coexecution tool. This tool is used as base to make the load balancing with CPU and FPGA, but this was originally developed by the University of Cantabria, supporting the CPU and the GPU devices. This tool has three kinds of schedulers: the static, the dynamic, and the H-guided. Schedulers are used to automatically distribute the workload among devices, in this case a CPU and a GPU. The static scheduler divides the problem in two parts, assigning a percentage of the workload to each device. The dynamic scheduler divides the iteration space in small chunks, which are dynamically assigned to each device when one of the devices is idle. The last, H-guided, is a bit more complex, starting with a big chunk size according to the computed power, and start to be reduce the packet size according to the equation with a factor k, trying that the device finish at the same time, reducing the unbalancing. Now, to adapt the Coexecution runtime to a CPU plus FPGA device, we follow 4 steps. Since FPGA in one API does not support another devices, the CPU one API code had to be ported to a C++ native code. Second, since C++ doesn't have a parallel for pattern, the new code should be parallelized. In this case, we use a thread pool. The 3 and 4 steps are about the FPGA. The GPU device was changed by a FPGA, and although one API idea is the portability of the code, the FPGA one API codes needs to be optimized to increase performance. All the changes that we apply in the Coexecutor tool are reflected in the scheduler. The most evident is that the CPU now is going to manage the number of threads that the user assigned. In this case, we have to change even the equation in H-guided to make a good distribution of the load. With all the system configured for a CPU and an FPGA, let's talk about the experiments. We use an Intel Xeon Bronze processor as CPU and an Intel Stratis 10 GX as FPGA. As software, we use ONAP 2021 version and Quartus 20.2. The load balancing was evaluated in 5 benchmarks, where MATAD and VAB need low computational intensity, Gaussian is an intermediate stage, and MATMULAN and MODI demands more computation. The result for a CPU won a C++ native version with one thread in blue, the one API version for CPU in orange, and the one API version of FPGA in gray are compared. In a benchmark with load computation as MATAD, the execution time is low in a C++ version for CPU compared with a one API version because the overload of communication with the host is high. In a computational intensive as N-body, the execution time is high for a C++ version, showing the FPGA as a proximity option with an speed up around 4 times. In the case of one API, comparing with the C++ version, it has a maximum speed up of 13.2. Increasing the amount of threads in the CPU, the tendency changes. The native version in MATAD and N-body are more efficient, increasing the performance until 6 times, which is equivalent to the number of threads in the CPU. Optimizing the FPGA kernel with strategies as SMD, unroll, and memory access, the kernels can achieve a speed up of 100 times. With this optimization and comparing with the CPU, the FPGA can be 15 times better than the CPU, but in other cases, as in N-body, the FPGA is worse. Evaluating the cooperative execution with the optimized version for CPU using 6 threads and the best kernel for FPGA, first we show the static scheduler changing the amount of workload in the steps of 10%. In the figure, the light blue represents the imbalancing between devices, and one of the objectives of the scheduler is to minimize it. The use of the scheduler in benchmark with low computation decreases the system performance since the overhead of the runtime and communication with hosts are more significant than the computation. In high and intermediate intensive computation benchmarks as MATMUL and Gaussian, the cooperation improves the execution time 80% for MATMUL and 30% in Gaussian. In the dynamic, the amount of chunks is varied in the x-axis, and the percentage of workload assigned to the CPU is shown under the benchmark title. In this case, with a low number of chunks, the CPU with its threads can get more workload and balance the system. Instead, increasing the number of chunks reduces the imbalance between the devices. In HI-guided, the parameter key is evaluated. Since the parameter can modify the number of chunks, in this case the CPU dominates the total time and the variation in the term does not show a significant impact. For this reason, this case should be studied in more details. Finally, as conclusion, in this work, the cooperative execution compared with the best device, it can achieve a maximum speedup of 26%, and the schedulers can achieve a maximum 95% of heterogeneous efficiency. To the best of our knowledge, this is the first work that combines CPU and FPGA under the one API tool working cooperative and mixing CPU and C++ multithread. To resume, not in all the cases the cooperation is the best option, as in the kernels with low intensity, but this approach shows how all the device can be exploited and cooperate efficiently. Thank you for your attention.